Everybody. It looks like we have about 40 participants on already, and the number's been climbing steadily. So hopefully we'll have more in just a few minutes. Good afternoon. Today is the second in a series of 5 webinar presentations in Vermont Public Utility Commission case number 21-3883-rule, which the Commission opened to develop a rule for energy storage facilities as directed by the legislature in Act 54 of the 2021 legislative session. The Commission is hosting this 5-part webinar series in conjunction with the U.S. Department of Energy Office of Electricity Energy Storage Program and Sandia National Laboratories. We are conducting this webinar series remotely using the Teams platform. We will be recording these presentations and making them available to the public as soon as we can post them. We will provide information on how to access the recordings as soon as possible. If you do experience technical difficulties today, I encourage you to try and reconnect to the platform. Given the large number of attendees, we will not be able to halt the presentations for any one person that is experiencing difficulty with their connection. In the event someone is unable to reconnect, they will have access to the recordings of each session once they are posted. Please keep your cameras and microphones turned off during the presentation to help conserve bandwidth and screen real estate. My name is John Cotter. I'm a staff attorney and Deputy General Counsel at the Vermont Public Utility Commission. I am joined today by Mary Jo Krolewski, Utilities Analyst, and Dominic Gotti, Department of Energy Clean Energy Innovator Fellow. Before we get started, I would like to thank, on behalf of the entire Commission, our colleagues at Sandia National Laboratories that have been working with us to make these presentations possible. Today's presentations will cover part 1 of a 2-part session on the installation and operation of energy storage systems, and will include discussion of safety codes and standards, interconnection requirements, and decommissioning considerations. Your presenters today will be Mr. Chris Searles and Mr. Charlie Vartanian. I will now give a brief summary of their backgrounds, which will not quite do justice to all of their accomplishments. Mr. Searles has been engaged in the DC power systems and stationary battery industry for the past 40+ years and has held key technical and management positions for divisions of IBM Corporation, Northern Telecom, ITT Power Systems, and Enersys, plus 16 years as North American Director of Business Development with BAE Batteries USA. Mr. Searles is currently an independent consultant with special codes and standards responsibilities for Sandia National Laboratories and the Institute of Electrical and Electronics Engineers, Energy Storage and Stationary Battery Committee. Mr. Vartanian has over 25 years of experience deploying advanced grid technologies, performing electric system studies, and contributing to technical standards development. He was most recently a senior technical advisor at the Pacific Northwest National Laboratory, supporting research and development to improve the reliability and integration of grid-connected energy storage systems. He also worked previously for Mitsubishi Electric, DNV KEMA, A123 Systems, Enron, the California Energy Commission, and Southern California Edison. He is currently secretary of the IEEE working group that is revising the Guide for Interconnection of Intentional Islands and is vice chair of the IEEE Energy Storage Collaboration Team. Charlie is a licensed professional electrical engineer and a senior member of the IEEE. We will have approximately 10 minutes for questions and answers at the end of each of their presentations. If we get more questions than time allows, we will be prioritizing questions from those who have been actively participating in the rulemaking process in case number 21-3883. If you do have a question, please enter it into the chat function and make sure to type in your name and your affiliation before you begin typing your question. Please understand that this is not an opportunity to express opinions or offer comments. Rather, it is an opportunity to ask clarifying questions in response to the materials you hear today. We will be establishing a schedule for moving the rulemaking process forward after we conclude this webinar series, and there will be opportunities at that time for providing comments and recommendations on what the rules should include. And of course, you are always welcome to file public comments into the case at any time. With all that said, I will hand things over to Chris Searles for our first presentation. Chris?
Okay, well, thank you, Mr. Cotter. I assume my slides will come up, or do I just do this?
I will leave that to Dylan Poindexter. He's the master of our platform.
No problem. Chris, would you mind resharing? I commandeered the screen for a minute, so you have to click reshare.
Okay, well, give me a second and I'll do that.
And I'll make a quick note. If there's a Jonathan Dowds in the crowd, if you wouldn't mind, please turning off your camera to preserve bandwidth, that would be great.
All right, I'll just use my camera here to introduce myself, and then I'll close my camera as well. But thank you for that introduction. Yeah, I'm past chair of the IEEE Energy Storage and Stationary Battery Committee, and currently co-chair with the IEEE Energy Storage and actually the ICS that gets involved with making our position statements for IEEE clear to NFPA. And so it's a pleasure to be a part of this discussion today. Actually, I was a little disappointed to learn that this was not going to be an in-person meeting, as I taught my wife and young children how to ski in Killington. And I spent the Christmas holiday that year at a very charming and rustic New England inn in downtown Rutland. And I kept kidding my wife. She didn't always agree with me that when I was ready to hang up my gloves and get a retirement going in action, I'd like to have a retirement place up in the northern mountains of Vermont. So I'm happy in that regard to be working with this presentation today. Now I'm going to shut my camera off just to save bandwidth. And now how do I get to my slides, Dylan?
So at the top, you're going to have to click share again, and it'll ask you what you want to share, and then you'll choose your slides. Awesome. Can you do the swap screen thing for me as well at the top with display settings?
That's where I don't see it here in this thing. Oh,
it's on your presenter one. Yeah.
Okay. Do I close this then?
On your screen with the presenter mode. Do you still see that? Yeah. Go back.
Oh, Dylan, we had this all set up.
And okay, on that screen, go to the top under display settings.
Well, I'll have to make this full screen, I guess.
No. Yeah, no, it'll be fine. Display settings at the top, please.
I don't see display settings up here. To be truthful, I see chat people.
No. You on the screen on the window with the two presentation modes open.
Oh, okay.
There's a big screen and a little screen. Yeah. Okay, at the top there, display settings and then swap screen.
Oh, okay. I'm sorry.
All good. All good.
All right.
There we go. All right. Thank you.
All right. Well, we'll start the time clock now, right?
Yeah, exactly. Go for it.
In January 1969, David Rubin, a medical doctor, published a book entitled Everything You Always Wanted to Know About Sex, but Were Afraid to Ask. I thought about naming this talk Everything You Wanted to Know About Energy Storage Safety Codes, but weren't really quite sure whether you really wanted to ask. But as you'll note from my talk, today I'd like to speak about the realm of energy storage safety codes and standards and give you an overview of the landscape, and then discuss how straight is the real way to accomplishing the objective of successful energy storage and safe energy storage installations. Permit me to start with an anomaly with a safety standard. The picture on the left is something that none of us like to see, but they happen quite frequently, where a major accident occurred with some fatalities that occurred. And that resulted in a safety reaction, as you see on the right, where either a regulatory agency or a city government or the railroad itself erected a safety reaction that included putting up warning lights and towering gates that would come down to prevent idiots from crossing the train track when a train was coming down. I think safety standards, in a way, are much like this analogy because we're more often really talking about a reactive result, a standard that occurs as a result of something that occurred, rather than a proactive action. Now, there's certainly a place for research and development in the future focus for safety codes. I think we all agree that lead acid batteries have largely addressed and really proven that they're basically safe because of their experience with hundreds of thousands of installations, millions of cells around the world, and standards have been put in place over the years to accommodate the issues that arise there. But with some of the new things that are happening, like electric vehicles with large scale utility scale battery energy storage, with the new emphasis on long duration energy storage, these are new in their embryonic phase, just beginning to be seen and addressed. So we also have the advent of new technologies that are being introduced into this space. Commercially available now are flow batteries. There's work and development going on in lithium metal, zinc or sodium ion, lithium or zinc air. Hydrogen is a big topic of conversation for long duration energy storage, coupled as a part of a fuel cell. And then we have new technologies that are really old technologies reinvented, like sodium nickel chloride and others. So there's certainly work to be done in this area. And then with the actual advent of long duration storage, targeting non-traditional locations that are meant to meet zero carbon and other types of goals, we are faced with the obligation, really, the requirement of putting these systems into high population or certainly dense areas. They aren't always the highest population by its immediacy, but they involve very large battery systems and sophisticated high power electronics. So this leads us to some questions that really need answers. How do we identify safety issues ahead of the experience curve? Can we get ahead of it and really provide some guidance before these technologies get into the market? And if so, how do we do it? Is full-scale testing necessary instead of current cell unit level testing? And if so, how do we do that? Because that would involve tremendous resources, number of personnel, much larger equipment, and obviously a large expense. And then how do we get the standards development organizations, the regulatory bodies like the PUCs and AHJs to fast track codes and standards to validate new technologies while ensuring their integrity? Well, I'm afraid, unfortunately, I can't answer those questions today, but let's transition to what safety codes can provide today, okay? Now, I think in my mind, there are several general categories of current safety codes and standards. At the top of the scale is fire protection and safety. And this includes not only fire suppression, but with the advent of some of the newer technologies, and especially lithium, we need to now take a very careful look at explosion control. And then we have the occupational risks and hazards that are covered by things like OSHA and NFPA 70E that include not only worker, but workplace safety as well. And then we have the design and material safety. How do we make sure that the components and materials that we're putting into the components actually are safe? And as we try to basically eliminate as much expense as possible, in other words, lower costs, how do we make sure that those products are not only safe, but that they're going to work and do what we say they're going to do and be reliable for the time period specified. So this leads to inspection, testing, and maintenance with requirements that not only need to be done at the beginning of the process, but also throughout the process as replacements or repairs or updates or companies go out of business. So how do we make sure that audits are performed in a meaningful and a reasonable way that ensure the integrity and safety of the installations? And then finally, we need to think about environmental safety. Not only the infrastructure for build and the infrastructure uh, in the environment, but the buildings and associated things with it, but also the transportation and over the highways and by air. I was a little surprised to see last week that JetBlue plane that took off from JFK on its way to Fort Lauderdale, and there was an explosion and fire in that plane. Now they were on the ground, and it being a consumer product with a lower kilowatt hour rating, they were able to put it out with water, um, and that's okay. But I understand there may be about one of these per week across the world of incidents like this. So environmental safety is certainly something that we really need to pay attention to. Okay, so if I were to ask you and a question, what would you consider to be the number one issue that you feel is important for battery energy storage systems? Now, I respect that there's probably a diversity of opinion, and if we took a poll, we'd probably get a number of diverse answers. But in my mind, the battery number one issue for BAS best systems, we call them, is safety. And on the screen, of course, I've chosen to show a few things that we haven't had a lot of ability to see a lot of the um, incidents that have occurred. A lot of these do involve lithium ion batteries, but high temperature sodium sulfur batteries and other technologies that are susceptible to thermal runaway and or explosion are things that make safety to me the number one issue that needs to be resolved. Will it always be the number one issue? Well, hopefully we get to a point where we have a good working stream like we have with lead acid batteries. Now, the history of fire safety and codes and standards has an interesting history. Actually, in Western civilization, the first known issue with codes and standards came about in Rome in 64 AD. Very elementary, obviously, but it involved a widening of streets, put some restrictions on home heights, and then said, hey, if we're really putting batteries together in a compressed environment, I'm sorry, not batteries, buildings in a compressed environment, then we need to make sure that we're using resistant building materials like stone instead of wood. Now, there was a big fire in London that occurred in 1666. It started in a bakery and basically swelled through the whole city and destroyed 80% of the city. What was amazing in that case was the fact that there were no real relevant new standards or restrictions that came out of that fire. But in the late 19th and early 20th century, we had a number of fires in the United States. Two notable ones were in Chicago, the 1871 Great Chicago Fire, and then a fire in 1903 that killed 600 people in the theater. And that led to some new standards that really involve buildings and egress and codes that would restrict making sure that we were trying to make people safe. But there have been other incidents along the way, but a lot has been done over the last 2 centuries. And in 2023, we have a fairly well established, instable vernacular, if you will, of a number of safety codes and standards. So, what are the current challenges that we face when it comes to battery and especially with energy storage? Well, I think definitely assuring safety against fire and explosions due to rash of incidents in many parts of the world in the last several years, especially with the lithium battery, but also high temperature BES batteries as well. And sodium is a big one in that arena. We also want to face the challenge of new applications such as distributed energy resources, which have evolved into creating microgrids that are used in residential homes, in community and commercial complexes, and even in high-rise buildings. And a microgrid really is, by definition, generally considered islanding, which means that we can go either standalone and create our own energy system, and there are a number of people that are doing that now, or we can have a solar system with batteries that's connected to the grid. So these are new applications that we need to understand and make sure that we do have the proper safety elements in place to protect and keep people safe. And then we need to worry about first responders, not only the firefighters, but the ambulance drivers and the medical assistants and the people that are brought to large incidents when they occur. Now, of course, our goal is to eliminate all these over time, but they are occurring, and we need to understand and make sure that we're adopting standards in a way that allow to protect these first responders. Now, the NNFPA actually, interestingly, began as a result of the first automatic sprinkler system that was patented in 1872, and it played a role in the creation of the National Fire Protection Association. The NFPA was actually officially formed when a number of insurance and financial groups meeting in New York City were appealing for fire protection regulations to be written. Now, without diving too deeply into the historical creation of the NFPA, the first standard that they came out with under their flag was NFPA 13. That's what it's called today. And it dealt with fire suppression, followed by what eventually became the National Electrical Code that is NFPA 70, and that came about in 1911. So electricity and water were really the accelerants that served as a backdrop to fire protection and guided the NFPA's creation. On the other hand, the story of the International Code Council, or ICC, while similar with mergers in purpose, is somewhat different. Three fairly large building code conferences merged at the behest of the building design and construction industry in 1994, and the first I-Code, now known as the International Building Code, was published in 1995. The International Fire Code and the International Residential Code evolved and were first they were first published in 2000, and they became known as the in some circles as the three model I-Codes. Okay, but I said my topic was on understanding, giving an overview, and determining which way is straight. Well, as you'll see on the screen, there are four paths out of the central hub of energy storage systems. We have NFPA up at the top and their roadmap out. We have the ICC over on the right and the three model codes. We have to involve UL because the UL laboratories are very heavily involved with certain standards that play central to all the others that you see on the screen. And then we have a couple of kind of regional state entities over on the left that have taken certain of the national codes and created their own codes, the New York City Fire Department and the State of California Fire Marshal's Office. So, whoa, how did I get there? Hang on with me a minute. Apologize for that. So, unfortunately, we'd like to say that all roads lead to Rome, but in this case, all roads don't really lead to Rome. And if you'll notice over on the right, there are some clouds that list a number of agencies and organizations, some federal, some standards development organizations like IEEE, some global, and some that are insurance related, and an alliance that basically puts standards and codes together that all want to have their positions understood and integrated in the code's working space. So this has raised a great level of interest in codes and standards. And before we really get started into a few of the nuts and bolts of the standards themselves, let me point out that there is a difference, even though we tend to synonymously use the terms. There is a technical difference between a code and a standard. And if we go to the NFPA Reporter's Guide about codes and standards, they basically identify that a code, and I'm not going to read the whole text here, but it defines the what of the code. In other words, this is what we really want to accomplish. And we're depending on knowledgeable people to make those recommendations. And it really doesn't become a law until it is adopted into a law. And we'll talk about that more in a second. A standard, on the other hand, tends to be a much more detailed elaboration. It's the how. This tells you how you go about doing what we told you in the code we wanted you to do. Now, everything in a code is a shall. It's determined by shall. It's not a maybe. It's not a could. It's not a recommended guide. It's a shall. Non-mandatory provisions are located in appendixes or annexes or footnotes or informational notes, and this is defined in NFPA 855 section 3.2.6. But the key point here is that neither becomes a law until it's adopted by a regulatory authority. Now, how does a code get implemented? Well, excuse me, let's take as an example the two codes that are the master fire codes, national fire codes, NFPA 1 and the International Fire Code, often referenced as the IFC. Now, inside that code, they contain references to a standard. And in this example, we'll use NFPA 855. As you'll see in a moment, there can be a multitude of codes. But anyway, those standards get referenced inside the code, and the AHJ, or regulatory adoption, the authority having jurisdiction, or the regulatory agency, adopts and makes the law, if you will, the regulation that's adopted, and that really becomes then the regulatory requirement for following those codes. Now, a code is enforceable, as I said, when adopted by the HJ or the regulatory agency. This leads to the first challenge facing NFPA 855, the first red flag, if you will. And as I mentioned earlier, I was going to point out that there are 21 NFPA standards referenced in 855-2020 and 10 UL standards plus 9 other reference standards in section 2.7 of the most recent 855 standard. So on the screen, I'm showing you a map. I'm not sure that this is the most current map. In recent research in the last few weeks, I found out that there may actually be 11 instead of 8 states that follow the NFPA 1 Fire Code, the National Fire Code. The other states follow the IFC, as does Puerto Rico and the District of Columbia and the Virgin Islands. All right. Now, the good news is, from my perspective, for you folks, is that you are following NFPA 1. But let me add some layers of complexity into the equation, okay? The first thing that we're going to talk about is that all states do not follow the same revision level, okay? In fact, I checked the Vermont Accepted Codes and Standards website, which state the same information as the NFPA Fire Code status of state's website. And if accurate, it appears to show that Vermont is still following the 2015 edition of NFPA 1. Now we have 2018 and we have 2021, and we have now the new standard that's just been published and is available on the NFPA website for purchase or acquisition right now, and that's NFPA 1 2024. Now, I'm not saying this to throw any stones here. It's just that if that's a fact, that's where you are. And that's the revision level. And that is an issue that we do have because many states, not just Vermont, probably the majority of states, aren't necessarily following the most current revisions. Now, the two that we know are California and New York. And I think Hawaii is following the most current standards. But outside of that, without doing a little more research, I can't tell you where it's available and it's on the website, but that's a fact. Now, the second issue that adds a layer of complexity is that many cities and states have their own code. Seattle, Portland, Oregon, Miami, other cities like New York have their own code. And they may use the IFC or NFPA 1 as a baseline, but then they really are only adding elements of these codes to their own code. And then to just put a little icing on the cake, some adopt only a portion or limited sections of the IFC or the NFPA codes in themselves. So let's put that aside for a minute because that's just the facts of the matter and that's the status that makes it complex. Let's talk a little bit about NFPA 855 because in the industry, within the battery industry, within the standards development organization, industries and organizations, and with the public at large, I think, that has reason to be involved with these codes and standards. NFPA 855 is becoming known as the bellwether standard for energy storage systems. And I'll explain that, why it's systems and not just installations in a minute. Now, they're dependent on the two codes that we've been talking about, the IFC and the NFPA 1. Now, we do need to add UL 9540 into the equation because it is referenced in all of the standards and codes that the standard and the two codes that we're talking about, and points to 9540 as a necessary listing that is required in order for your energy storage system to be qualified and compliant with 855. Okay, but let's dive a little deeper. So we have NFPA 855 as the bellwether, but remember I said there were reference standards within the codes and even within the standards, we have references to other standards. And in the NFPA case, we have the fire code. We also have the National Electric Code and two subsets of that, the maintenance code and worker protection and safety code 70E that deals with arc flash and PPE and things of that nature. And then we have two codes that now are a part of the 855 standard, NFPA 68 and 69, which deal with explosion control and or basically making sure that there's ventilation, configuration that gets rid of toxic gases. But we have some other elements we have to concern ourselves we'll talk about in a minute. And then NFPA 5000 is the equivalent for NFPA to the International Building Code, but it really plays a much more minor role. Then we have within UL 9540, it points to a number of other standards. 9540A is not a standard or a guide or even a testing requirement. It is considered a document, perhaps a guide, that leads lithium and anybody that wants to get the UL 9540 certification following a hazard mitigation analysis compliance testing that shows that your energy storage system, and it is a system document, basically will not spread a fire and now explosion beyond the confines of the unit or module or rack that this system is contained in. UL 1973 has listing requirements for battery and BES components. It is considered a standby battery application standard, but is enlarged now to incorporate energy storage testing, and the lead acid as well as lithium and sodium metal chloride and other technologies must comply with testing requirements under 1973 that feeds into 9540. 1642 is going through, it's the lithium cell standard. It's now going to probably roll into 1973, and UL 1778 is the UPS standard. Then we have the ICC, the three I codes that we talked about. And all three of these have an interrelationship among themselves, but we also have two IEEE standards. One is really a best practice that is in the process of being considered as a standard. 1547, that I think Charlie, who's my partner, going to present after me today, is going to talk to you a little bit about that and the standards that roll into NERC and FERC. But IEEE 1635 is a ventilation standard that will have some relationship in the future to NFPA 68 and 69. And then we have the IEC, and UL and CSA, the Canadian group, are actually working on committees with IEC, and actually a couple of national lab people are involved in these committees. The big banner is IEC TC 120, but UL is adopting some of these standards, maybe making minor modifications to incorporate into the North American complex. And they are coming out with this 600 series of standards. These three right now are the ones that applied peripherally to energy storage. So we'll give them a dotted line and let them connect too, because they're certainly going to be important as the future unfolds. Okay, this project began as a project requested by the California Energy Storage Alliance. And I'm talking about the development of the 855 standard. It started in early 2016 and was undertaken by the Department of Energy. And as I learned recently, the Sandia National Labs, as I understand it, and the Research Foundation of the National Fire Protection Association. While the Alliance's concern was definitely the rising use of lithium in the traditional lead acid space, the potential for other electrochemical technologies that were in embryonic forms of development and deployment, most notably high temperature sodium sulfur, or the NAS battery as it is called, and now flow batteries, became concerns. This led eventually to the regional release of NFPA 855 at the end of 2019. It was a very contentious committee that dealt with the first revision, but the NFPA Standards Council decided that rather than send it back to committee and wait for another year or three, possibly, to iron out differences before a release, it was issued without a scope, perhaps the only NFPA standard to do so. However, the 2023 release, effective in September last year, not only now has a scope, but has made several improvements built on lessons learned from the serious incident at the McMicken plant in Surprise, Arizona, and a number of other incidents in Korea and China as well. Okay, so let me begin this next phase with an acknowledgement. It may impact the ability, and I understand from the opening remarks, this is being recorded, which kind of gives me a concern. References in quote marks taken directly from NFPA 855-2023 are copyrighted and are shown in this presentation for educational reference only and cannot be copied for distribution. I need to explain that you can get access to all the NFPA codes free of charge. And by the way, if you subscribe to the NFPA link, as I do, you're able to download any codes that are listed, and all the NFPA codes are there. um, for your own personal use. I have incorporated a few of these, and I may have overkilled the way I'm doing it, but I don't want to go to jail. So I'm going to show you a few things that are copied from the code, but I really ask that if you do have access to these, that you do not distribute them. Okay, let's start with the scope. This scope is new to the 855-2023. Now, what I want you to notice is that it doesn't apply just to installation. It applies to the design, the construction, the commissioning, the operation, the maintenance and decommissioning of the stationary energy storage systems, including mobile and portable ESS installed in a stationary situation, and the storage of lithium metal or lithium batteries. Now, I need to point out that portable ESSs are mobile. Electric vehicles are mobile. This standard does not deal with EV or EV to grid type of standards. It does, though, deal with stationary energy EV charging stations. Okay, the purpose is enunciated in section 1.2. And here I just want you to realize that this is a minimum set of requirements. In other words, as New York City and maybe California and perhaps some others have done, you can go beyond the minimum standards and provide maximum requirements for that matter. But the bottom line is its purpose is to mitigate the hazards that are associated with these systems and deal with the new problem we have with reignition possibilities with lithium metal, especially if they're in storage or in places where the kilowatt energy level is higher than a minimum level that will ensure making sure that we don't have a major problem. Okay, section .13 then establishes some values that are shown in a table that basically say that if you go beyond these values, then this standard applies. And that table is shown here. This is not the actual table. This is a facsimile of it that I created. I added the line of the batteries for 1 and 2 family dwellings, but it does show the measurements in kilowatt hours and megajoules. And that is the terms that the Standards Councils and industry at large now uses. I'm not going to get into definition of the terms. Let it suffice to say at this point that a kilowatt hour represents 1,000 watts of power that can actually supply capacity to a load for 1 hour. So as you can see, lead acid and NiCad can do 70,000 kilowatts for 1 hour. A lithium, if it goes over 20 kilowatt hours, must 20,000 hours for an hour, kilowatts for an hour, then this standard applies. All right. New technologies that may come on the scene will be restricted if they're energy storage systems to 70 kilowatts hours. Capacitors and batteries in family dwellings are much lower. Okay, there are a few key definitions that I think are important that I'd like to preview with you. Again, these are copyrighted, so please don't distribute them unless you get the standard. 1 or more devices assembled together capable of storing energy to supply electrical energy at a future time. That's kind of pretty basic, isn't it? In fact, the dictionary has that definition, I think. But the fact is that energy storage really, as you're going to see, involves all applications where batteries, whether they're standby or in partial state of charge or what we call cycling applications, they are covered under this standard as defined here. A fire area is an important thing to understand. This is an area of a building separated from the remainder of the building by construction that has a fire resistance of at least 1 hour, that basically says that that fire can't go beyond where it is for 1 hour, and all communicating openings properly protected by an assembly having a fire resistance rating of at least 1 hour. There's actually some language now that's going to 2 hours in some circumstances, but right now, 855-2023 has 1 hour. Hazard mitigation analysis and evaluation of potential energy storage system failure modes and the safety-related consequences attributed to the failures. I meant to say at the beginning of this that this is, in my mind, one of the most important definitions in the standard because it is fundamental to the actual creation that allows, whether you're a manufacturer, a developer, an installer, an AHJ, approving the installation of, getting involved with a energy storage system. This document is the basis that goes into understanding the 9540A testing that you would do that allows you to get your 9540 certification. And it is referenced heavily in the 855 standard and is referenced in NFPA 1, not necessarily IFC yet. We'll talk about that later. Okay, maximum stored energy. This is a term that's important to understand as well. It's the quantity of energy storage permitted in a fire area prior to that area being considered a high hazard occupancy. I'll show you a chart in a minute that it defines that a little better. This term was added into the 2023 involvement. I am sort of a lead acid, call me a specialist, not an expert, but because you never become an expert in batteries, I don't think. But I'm involved with the 855 committee as well and the FCAC on IFC. Standby power applications got put into the 2023 standard of 855 to differentiate that they could apply to certain carve-outs for certain batteries that we'll talk about a little later in the presentation. So the difference between a standby power application and a new energy storage application really only means that in a standby application, we're keeping the battery on charge continuously, and it's able to supply, or it's supposed to be able to supply, its full capacity rating for the time that you specified the battery had to support the loads you're keeping, or critical loads that you can't afford to have go down. In an energy storage application, there's a lot of cycling involved, which may involve partial states of charge, and they're differentiated in standby, but with some technologies, the technologies are the same and it muddies the water. That's one of the complexities of this whole circumstance. Thermal runaway has been defined within 855. There are different definitions out there, but self-heating of an electrochemical system in an uncontrollable fashion. With a lithium battery, you may have a thermal runaway condition without necessarily creating a fire, but you could have the release of toxic gases and could actually have an explosion without a fire. It may be a little bit unusual, but it can happen. So thermal runaway in 855 context is a thermal event that really gets started with an individual cell or battery module, and it gets a runaway condition in an uncontrollable fashion. It may or may not involve a fire. We're looking at introducing a new term called thermal walkaway, which may help to provide a distinction between these two. Now, the key elements, I talked a little bit a moment ago about table 941, defining an allowable maximum stored energy. I'm not going to go through all the notes. You can glance at them quickly. This again is a facsimile, not the exact table, but the data is accurate. Lead acid and NiCad batteries and other nickel technologies really aren't restricted on the number of kilowatt hours that they can put in a given configuration outdoors. Lithium ion has a 600 along with sodium nickel chloride. Flow batteries are all at 600 kilowatt hours. These can be converted to watts per hour or ampere hours, as I may or may not have mentioned earlier, but there are formulas that allow you to do that. And then in a family dwelling where this is becoming a big issue now because so many people are adding batteries to their solar panels, they're restricted to 80 kilowatt hours without making sure that they go through and are compliant with 9540. And then you see the others there. Okay. So what are the key elements in 855 that I'd like to make you aware of? Well, as I've said over and over, it applies to all energy storage applications, but there are some carve-outs for lead acid and NiCad. It now covers all commercially available technologies. Originally, it really was intended, I think, to apply to lithium, sodium, lead acid, and NiCads and flow batteries, but now a number of other technologies have been introduced, including the mechanical flywheel. So it's not all battery technologies, mechanical flywheel. And there is a section that's reserved for supercapacitor that's coming. It requires UL listings for all devices used in these applications. That includes standby and the new ESS. And it does involve anything that goes into that system, not only the battery, but inverters and UPS devices and controllers and any of the power control equipment, disconnects, all of these. And this is not necessarily introducing stuff that hasn't already been a part of the National Electrical Code. But the bottom line now, it is a part of UL 9540, and it is a requirement in order to pass the testing to get the UL 9540 listing. Okay, I keep hitting the wrong button. Sorry about that. Thermal runaway and explosion testing as required by 9540A is a part of the standard. Explosion protection by deflagration, which is venting of toxic gases. And there is some issues over plumes and how far they should extend and display bond entrance boundaries. NFPA 68 deals with that. NFPA 69 deals with the actual control or prevention of it. But there's some discussion going on now that NFPA 69 may be deleted from the 2026 edition because of the issues that are technical in nature. And there is some discussion going on where it can apply, as opposed to dumping hundreds of thousands or millions of gallons of water on a lithium ion or thermal energy susceptible to a fire or explosion technology. Dumping all that water on it because there are environmental issues involved with that. Maybe to let it burn, but you can't always let it burn. So NFPA 68 and 69 are right now required in 2023, but we may go back to saying only NFPA 68 is the standard that applies in these cases. These standards are available from NFPA, and they can be looked at free of charge if you register and sign up as you do, as I mentioned earlier. You already have a section coming up on interconnection and commissioning and decommissioning. That's certainly an important element of the whole scenario. Some interesting highlights. We've taken all the sections that related to electrical chemical technologies that were spread in all the chapters from 4 through 11 and put them into chapter 9. So now a user of NFPA 855 can go to chapter 9 and see what he needs to know about the electrochemical technology itself. There's an annex that I'll show you in a minute, but the bottom line is that we've consolidated that. There is this separate chapter that's been taken. We've made chapter 14 into a lithium metal, lithium ion battery storage chapter. And that's to deal with reignition and making sure that batteries in an indoor location that are stored are safe. Residential requirements have now been consolidated, as we did with the technologies in the first bullet. into chapter 15, though, not chapter 9. And then we have solid annex material in Annex B and Annex G. Actually, this is a copy of the 850. I didn't put the copyright on it. Well, it's not copyrighted because I had total number of pages down there. And by the way, they're parallel. But in summary, this gives you there are over 150 pages in my digital version, which I have been able to download offline through my subscription with NFPA Link. But the annexes really give you some excellent material. If you aren't willing to be an electrochemical chemist, don't want to be a physicist, don't really care about knowing everything there is to know about batteries, but we're afraid to ask, this annex material will give you an awful lot of good information. Annex A basically supports and gives clarification a lot of the shalls in the standard. Then Annex B really talks about various systems hazards with the various technologies. I actually wrote the section on lead acid batteries in Annex B. Annex D gives you a better overview of all the technologies that are contained in the energy storage equation, and including flywheels. So this is an excellent section to annex to read. And then
Hey,
one of
Chris.
the best
Hey,
sections in my mind.
Chris.
Am I running out of time?
Yeah, we're a little over 45 minutes. Are we close to the end?
Yeah, I'll highlight it very quickly. Okay.
Great,
Get
thank
your
you.
copy of this and then read Annex G. I think you'll find it very informative. Notice it's 53 pages. All right, we've already begun, and you can make your public inputs into comments into the new revision. It'll open in March of next year. You'll have till the end of May to do it. And then it'll be posted for a final review in February of 2025, goes through some process steps, and will be released in the fourth quarter of 2025. As I was just reprimanded for going overtime, I'm going to hide. There are these carve outs for lead acid and NiCad. They can become part of a separate session if you guys are interested at some future time. Let me summarize and offer a couple of conclusions. I think we all understand and agree that energy storage is going to be playing an ever increasing role in electrification and zero carbon goals. Uh, these codes and standards are going to be a critical piece of the overall equation, and NFPA 855 is going to be the go-to standard for these installations. Currently, I think we have to accept, at least we in the industry see it, that electrochemical technologies are going to be the main commercial devices for the immediate future. Now, the real question is, how do we define the word immediate? Because we thought this might take a decade or two before it really became mainstream, and it's already mainstream within the last decade. And then the new technologies are all jockeying to play a role, and we're going to have to watch them carefully and see how they can play in the mid to long duration energy storage markets. My conclusions are simple. Just like we've done here today, I believe, and I think most of my colleagues agree, that education and training is needed to bring ACE, and regulatory bodies up to speed on the NFPA and or ICC codes and standards with an incentive to update outdated editions to the current level. Now, I can't define what those incentives should be. I'm not even in a place to make them, but I think it would be good if we could incentivize everybody to get to the most current levels. The key players need to become involved with the key SDOs, primarily ICC and NFPA. And if you're not already engaged, it may be difficult to get into the 855 committee, but other committees like NFPA 1, 110, and IFC and the FCACs around them are pretty easy to get into right now. Then a means to correlate the varying editions versions of the interrelated standards to the same editions and reflection of requirements across the different regulatory bodies so ESS safety is offered on a level playing field is an important necessity in many of our minds. Okay, with that, I guess I'm done. I want to thank you for your attention. I hope this has been helpful and interesting. And if we have time, I'll certainly be glad, if I'm able, to answer any questions you have later on. Um, I'll get out of it and give it back to you, Dylan. Can you take it?
All right. Yeah, definitely. Chris, yeah, if you want to put your camera back on, that'd be great during the Q&A. All right. So I got a couple of questions for you in the chat. Can you hear me okay?
Yeah, okay.
Perfect. All right.
Uh,
So I've
by
got a
the
couple of,
way,
yeah, go for
let
it.
me get the camera. Yeah, let me get the camera. All right, there I am.
All right.
I would have had it on during the presentation, but you sort of indicated you wanted them off while we were giving the presentation. So,
Yeah, just it's just a precaution for, if bandwidth issues start acting up, it's a good way to help with that. But great to see your lovely face. I got a couple of questions for you. Firstly, being from Dominic Gaddy from the Vermont Public Utility Commission. He asks, can you talk more about fire areas and what a 1 hour fire resistance means for buildings?
well, I think most of this comes from the International Building Code, to be truthful, and maybe NFPA 5000. It's referenced in 855, and there are sections that deal with it. But my understanding is that we're talking about the wall material, the building material, the ceilings, the floors. We got to make sure that if a fire does erupt inside an area where an energy storage and battery system is involved, that it can be contained and not spread to another area for no more than 1 hour, or at least can't spread for at least one hour. Now, to be honest, am not, without looking it up, available to tell you the exact materials, but that's what it basically involves. Now, what that says is that if you've got an energy storage that goes beyond the maximum energy levels, that you have to put some distances into it. Unless you've gone through and have proved with 9548 testing and an HMA that you can put your units closer together than either 3 feet, depending on how you tested, or 10 feet, depending on lot lines and other things, then you have to spread out additional configurations up to maximum storage levels. So that's kind of the context. I don't know if I'm answering it correctly, but I think it gives you a perspective on what I'm talking about.
Great, thanks for that. Let's see. Got another question for you, Chris, from our next presenter, Charlie Vartanian from IEEE. He asks, what is your opinion on when solid state lithium ion based ESSs will be available? And what are your thoughts on if or how lithium ion safety risks are mitigated?
Well, Charlie, you come to our ESSB meetings, and you and I have worked together on several of the codes, including 1547.9. You know that that's the $95,000 question. It's even bigger than 64,000. There's varying opinions. Lithium metal, we thought might in the original stages not might actually be fire resistant, might have problems with fires. As it turns out, they can go into thermal runaway or have fires, so they're not perfect. Uh, Lithium iron phosphate is a much safer technology. Like lithium titanate actually is the best lithium technology out there, and if you wanted to use it, would be the safest. But it's expensive, it's highly dense, and you'd probably go back to a lead acid battery rather than going to lithium titanate. But lithium manganese and lithium oxide, those cobalt, they are much more prone to problems than lithium iron phosphate. But you have to get underneath the technical details. As far as how soon the lithium things can be brought under control, boy, there's some people here that may be better subject matter experts on that than I am. I couldn't answer that question.
Great, thanks, Chris. And I got one more for you if we can answer that pretty quickly. Forgive me if I mispronounce the name. Vijay Vankela from the British Columbia Institute of Technology asks, can you comment on flow technology? Is the NFPA including special guidance for this, which shows different fire/explosion characteristics?
The answer is there is a full section on flow batteries in the body of 855, and yes, it is included. And IEEE actually is developing a standard now, 1679.3, in which it's chaired by a fellow from the P&L Labs up in Washington State. And they are really doing a deep dive into the various elements and variations of flow batteries and dealing with these very issues. And uh, if you send an email to Dylan and want information for a connection, we can put you in touch with those people and would love to have you get involved in that. We're developing that standard right now, probably going to ballot in the next year or so, and it will deal with the very questions you're asking.
All right. Thank you so much, Chris. Let's give him a big round of applause. That was a great presentation. I appreciate it. Just looking at time, I do want to go ahead and spin over to Charlie Vartanian from IEEE. Charlie, I believe you are willing to share your slides. So the floor is yours. Let me know if you need any help.
Thank you, Dylan. Let me go ahead and share my screen. And first, thanks to John Cotter, Dylan, and Will McNamara for organizing and giving guidance for today's event. And do want to congratulate the audience. You must be the most engaged stakeholders to sit through 2 hours of codes and standards discussion. So on to interconnection. Interconnection standards. And one guiding principle to today's talk is there are certain components of the Rule 5.500 interconnection rule proposed update that really map well and take advantage of the latest version of 1547-2018, which in part was driven to incorporate and address the capabilities of, quote, smart inverters, which your updated ruling calls out as an equipment type. So we will be hitting the IEEE 1547 standard for interconnecting DER with electric power systems, with a bit of a focus on how this is applied for energy storage. And there's some good news there. You don't need separate interconnection rules or necessarily even settings to incorporate ESDER as you would any DER onto a distribution system. This is an IEEE presentation. Although it doesn't represent IEEE itself, it's the view of the volunteers. And I do want to thank the volunteers who help create these standards and maintain them. So today, I want to give some background on what 1547-2018 is, the new edition of a guide for applying 1547 to energy storage, and then hit some specific challenges and outlook. What are challenges and mainly looking towards the implementation application. And then the outlook is what updates are coming up to IEEE 1547 and some related 1547 guides. This is not news to anyone, but it's still a foundational driver as the power system is still transitioning from central station created energy and power transmitted over wires to end users, pretty much one direction. The grid is in various stages of evolution to a much more bi-directional situation. We still have central station power, but you also have active loads and active resources out at grid edge and on the distribution and on the transmission along the whole delivery system. So early on to the rescue came IEEE 1547, and it really did facilitate inclusion. At this time, it was early stages of PV adoption by this national level legislation guiding or requiring states to at least evaluate and consider use of 1547 and setting their state jurisdictional rules. That really accelerated the consideration and then the adoption of IEEE 1547 as referenced and used in your Rule 5.500. Do you call it 5.500 to anyone who uses your rule?
Yes.
Thank you. I want to highlight what it is not. It's not any part of your interconnection agreement or even procedures from application through approval. Is a really handy reference, though, that those stakeholders involved in your specific process do and can continue to reference, especially as you move into a much more dynamic distribution system world. Also, another thing to keep in mind is this non-prescriptive. It sets the requirements. For example, unintentional islanding needs to be present for a compliant system. How you implement that is not prescribed. It is also technology neutral. So some people mistakenly believe this is an inverter standard for inverter-based resources. It is not. It is non-technical specific. So it applies to rotating machines as well as inverter-based resources. This is really why was IEEE 1547 updated? It was to better balance the still core requirement of safety, do no harm to grid safety and grid reliability. So by safety, it's primarily assuring that an otherwise system that's out and even isolated from a fault is not backfed and energized by a third party generator that the utility doesn't know about and expose the public and utility workers to a shock risk. The reliability is around making sure that the performance characteristics don't interfere with voltage, limit compliance, basically the whole host of reliability obligations that flow down to NERC, all the way down to distribution utilities that are keeping voltages within specified ranges and not impacting system frequency. But with increased penetration of renewables, there is an increasing need to have some capabilities that provide some grid performance support. And your proposed updated rule catches the big ones, ride through. Um, and we'll hit on that in a bit. What's great is to me, this is a real win-win. Newer technologies can deliver these many times as an inherent product capability. They just need to be specified and then implemented with these capabilities. It's minimal cost in many cases, and the return benefits are great to all sides. Great success in lifting, for example, renewable hosting capacity in a number of markets. California, Hawaii, great examples of earliest adopters of even before 1547, 2018 was approved. They had implemented their own tariff rules, Hawaii Rule 14 and California Rule 21, calling out specific smart grid capabilities that kept them ahead of, I'll call it, severe constraints on hosting capacity. IEEE 1547, for those who use it, a big other change in going from the 2003 to 2018 was the inclusion of interoperability. And there was a question in advance on communication protocols, and we'll touch on that. Because in the interoperability section, it calls out 4 specific protocols that through your Rule 5.5, calling out 1547's latest version, the 2018, that inherently requires the use of some core protocols that are common across the power industry as a capability. Now it's up to the AHJs, the connecting utilities, to determine what protocols to go from capability to requirement. So that's going to be something for your community to work through. No change to the scope in terms of really the 1547 doesn't put requirements on the delivering distribution system. I'd say, except for how performance is measured at the point of coupling, how an engineering firm, device, or system manufacturer implements within the fence line. 1547 doesn't get into that. It is really aimed at what are your communication capabilities at the interface and what are your impacts at the point of common coupling. typically the metering point. And we'll touch on the bulk system aspects as well in a bit, because that's where the drivers of ride through are really coming in. And what really looks appealing is the fact that you have a centralized transmission provider through the Vermont Electric Power Company, and the fact that the upstream ISO New England has already been very proactive about energy storage, hosting one of the first frequency regulation systems many years ago. A quick thought, we're going to come up, touch on certification. UL 1741 is the available and completely usable and very handy mechanism for certification. And that goes hand in hand. It is a certification for assuring that a listed device is compliant with 1547. Now here's the issue and the devil in the details for you all. You call out the latest version of UL 1741. Well, the latest version has 3 supplemental amendments. SA is compliant really with the pre-2018 requirements of California Rule 21 and Hawaii Rule 14. I'd say there's over 90% conformance or consistency with UL 1741 Supplemental Amendment SB, which is very recently approved, and in my opinion, not a lot of products certified to that yet. That SB amendment means it's certified fully to 1547 2018, and something to just keep in your hip pocket. UL is working through an additional amendment, SC, that will address grid power delivery capable vehicle to grid. So vehicle to home may not fall under it, but there's a lot of work going on between IEEE and SAE, and right now mainly charging equipment developers to make sure that bidirectional chargers that can reach out beyond the home or facility out to the grid are 1547 compliant, and UL is already working on that certification process. We're not going to go through all of these clauses. So instead of chapters, to keep it confusing, the terminology is IEEE calls each of these clauses. And we're only going to touch on a couple that, in my opinion, are really relevant to the updates going into your Rule 5.500. These are really remove unintended constraints. There used to be a 10 MVA limit to 1547 2003. That's removed. There is no capacity called out. It's any asset that connects to distribution. And I don't know if it's the case in Vermont, but for some radial subtransmission up to 115K, some of that can be defined as distribution. I think some of this just reiterates what I said earlier. It's not a design guide. It sets the performance requirements. It doesn't say how to implement or necessarily even how to use them. How do you turn a capability into an application? That's outside of 1547. Oops, I need to update that. Oh, the revision has begun. Um, that shouldn't be cause for too much worry, because that active revision of 2018 is mainly to address errors and to get some areas cleaned up that caused problems in implementing the UL 1741 SB testing. But areas of new material may be entered related to security and possibly energy storage, and we'll hit those. But in the interim, there aren't going to be massive changes that let's say diminish. If you want to reference SA or SB now, of course, this is my opinion. I'm not seeing anything on the revision that's going to completely rewrite the rules, so to speak, from a performance viewpoint. And if you're interested in what this revision group is and what they're doing, if you download the PAR, that gives the scope and purpose. This is, to me, a good example. If standards stay ahead of policy, you can avoid unintended barriers. So this is from a workshop I attended or it was just to socialize and sensitize the people working on the AB 2514. That legislation turned into a regulatory ruling to mandate energy storage procurement in California. That until 1547 was revised, or California Rule 21, these highlighted applications would have been in conflict with the standard. Rule 21 was updated in time, so these barriers were removed. And maybe I'll take this as a time to comment on this issue of standards can help, or how standards are referenced and used. You can remove unintended barriers. So you've got one area in the proposed ruling under preliminary screening criteria that proposed projects not affect the ability of interconnecting utilities to main C84.1 ranges. Those are the allowable voltage ranges. Inserting a word like negatively affect would leave open the opportunity that these voltage regulating assets, especially under high penetration, should be released to positively affect and support primary voltage distribution regulation, or at least considered, depending on the attributes of your system and the type of voltage regulation equipment and practices by the utilities. But that's just an example to throw out. The other one that jumped out to me was projects, screening criteria, projects not located in an area of known transmission stability limits. That's another case where inserting language like unless agreed upon by the two parties. There is a capability called fast frequency response that is going to mitigate as our system goes from central station high inertia machines to low or no inertia inverter based machines. This ability to stabilize the grid, including by DER, is being more and more recognized by even NERC, and they're going to set some fast frequency response requirements. They already have at balancing area level that will flow down to the transcos, and there could be a case where they pro rata assign some support to the discos. And this is a case where if you allow that ability for fast frequency response devices on weak systems, you can really get some benefit. So these are just ideas to throw out. As an IEEE volunteer, I'm really here to talk about what are the performance requirements. IEEE volunteers really in that role shouldn't be getting involved in the interpretation or the application. So consider these just ideas. So IEEE 1547 2018, that last update, I was among some people who tried to get some energy storage minimum requirements put in. That didn't make the cut. There were bigger fish to fry at the time, like getting the smart inverter input. So we really took the proposed chapters and turned them into a guide. Oh, do want to thank uh, Chris. He was either the current chair or past chair of ESSB committee that sponsored the creation of this guide. So the thing about IEEE standards, unless a technical committee really blesses it, it cannot move forward. So Chris was critical in making sure this did move forward. So to highlight areas that could be really become important to your market, black start. Energy storage as a black start device is going to be very handy. That's another area of looking now to see how you just avoid the ability to access if and when relevant to you. Clarifying voltage VAR support, volt VAR support modes for energy storage. Energy storage can, in its operational flexibility, goes beyond the operating curves of 1547-2018, and this guide really just shows how you would be 1547 compliant with the full four-quadrant device that is not just positive and negative injection for reactive, but positive and negative injection for real power. And again, by prudently accessing those capabilities, it extends that grid support goal that was part of the 1547 update. I'm trying to, ES terminology. And also, it gets into when is an energy storage within scope of 1547. And that's another area where this guide may come in handy. It keeps it real clear what in my mind, a bright line between what's a UPS that's not compliant or a V1G smart charging vehicle versus V2G they can deliver to the grid. And so that's another area of this standard to point out. To make it simple, 1547.9 does follow the clause or the chapter order and topics of 1547-2018. The one exception is clause 12 was added on safety, which Chris co-led. IEEE standards are not safety standards. That's the realm of NEC, NESC, and the safety, fire safety communities Chris works within. But with the issues with the prime mover batteries having unique safety attributes that are very different from other prime movers, what that chapter does is it just points to the appropriate safety codes, and it references that um, designers, deployers, connectors of these assets should be aware of. This is a very useful example, a very simple. Again, it's a guide. It's not a shall guidance, but I would argue it falls within the realm of good engineering practice in terms of screening what falls within being compliant within 1547 and what isn't. Operational state of charge. Um, There's a requirement in 1547-2018 that an energy storage unit must, through its new interoperability systems, report its state of charge. And they had the term operational state of charge. So Sandia National Lab wrote a really good appendix that's in 1547.9 that really firms up how you would define it in a way that implementers, testers, evaluators have a common understanding what we mean by operational state of charge. This is an example of getting around, uh, you know, when capability is bounded by a state of charge of an energy storage system. I'm not going to belabor this, but black start and intentional islanding, uh, it's an active industry issue in general. And these are some of the parts of 1547.9 that may move up into the renewed standards, just to impart and firm up some of the requirements that would enable this in a sensible way and in an, I'll call it a non-prescriptive way, up into the main standards. It's an example of getting 1547.9 expanded to include the full four quadrant capability of energy storage. And what's nice is there's really no change to 1547's core requirements except to make it a full four quadrant graphic and set of numbers. I just want to touch on this. Fast frequency response capability is required in IEEE 2800, which is the new inverter-based resource standard, interconnection standard for transmission connected. 1547.9 discusses it as a desirable capability. But depending on what the upstream people responsible for frequency regulation and frequency management sort of flow down, at least 1547.9 has a good discussion of what FFR is and how it relates to the performance capabilities of a 1547 compliant energy storage system. The good news is, if implemented consistent with the approach in IEEE 2800, there would be no conflicts with an energy storage system performing fast frequency response. It'd still be within 1547.9 performance standards in general. Already hit this point. Want to spend a little bit of time because there were questions that, and there's a portion in your proposed rulemaking on communication protocols. 1547.9, let me just jump down to the general. 1547-2018 lists out the accepted protocols. And one of the questions was more in context of what communication protocol is relevant to talking to the utility. In my opinion, DNP3 is still the dominant protocol used when talking to a asset, at the point of common coupling, either reporting out, metering information on its performance, or receiving dispatch instructions. The Modbus and the SEP2 are more in-plant protocols that many times are translated at the point of common coupling. But here's the point. These are already required as capabilities in the main standard 1547/2018, which I think is good news. Every inverter manufacturer that's now certifying to SB is assuring that they have this capability. So depending on what you call out in your jurisdiction, at least these three capabilities are there if you want to then require within your jurisdiction any specific capability. Again, and this capability is aimed at the interface. It's not telling the utility nor the plant owner operator what they use within their respective areas. This is really at that interface between the two. 1547.9 extends and adds some additional information objects that should be added to an energy storage system to the base set of information exchange called out in 1547. The 1547.9 slides were prepared by Mike Rock. He was the chair of the 1547.9 working group and still an active supporter of standards development via Sandia. And I welcome you to email questions, or I'm glad to take questions today. And Mike and my prior work were both supported by Dr. Emery Juk of the DOE Energy Storage Program. The last item, Dylan, I can't, a quick time check. How am I doing on time?
You're doing great on time. You can take an extra 15, 20 minutes if you really want to.
Oh, or people get an extra 5 minutes back, maybe. We'll see what
Okay.
happens with this section.
Sure.
Um, one of the guidance going into this was select some challenges and what's the outlook for interconnection standard going forward. So again, a little bit filtered by what I did got through a quick read through of your proposed updated rule 5.500. Here's some thoughts to share with you. And again, questions or corrections on my perception and what you're doing out there are most welcome. So this is Rule 21, or I'll call it 1547 working groups. When they wrapped up the update to the revision, they did do a nice survey facilitated by EPRI, where they canvassed all of the working group members and other interested parties. What remained their top concerns? And I'd just like to point out that unintentional islanding, cease to energize, that without galvanic separation, and this is relevant to you all, do you have to physically separate open contactors to cease to energize? There are inverter advocates that can argue really well that you can use control systems to assure you're not backfeeding and energizing a grid that is out. So those are still at the top. And here's something to consider. If you cease to energize by disconnecting and you're 1547 compliant, the standard or default return to service is 5 minutes. There's a lot of active work already out in the West and in other areas that as DER penetration goes up, that 5 minute pause to get assets back online to serve load is impacting frequency recovery after, let's say, transmission or bulk system level events. So IEEE 1547 2018 has two very useful aspects. You can cease to energize, and the keyword without tripping. If you trip, there's a return to service with that default 5 minute delay. But if you cease to energize, you can stay connected and synchronized as long as you're not transmitting real power, net power back to the grid. And there's some residual amount of reactive power you can transfer, but no real power. And that really improves the grid reliability, grid performance in an era of increasing distributed resource penetration. The other aspect is that 5 minute return to service. There's more language in 1547 2018 that allows along the lines of with agreement with the connecting utility that time to return to service can be shortened. A lot of concern as you start getting these DER that are riding through brief events. A lot of consideration, but still concern that the distribution system protection schemes that are letting ride through and system these DER ride through. I'll call it short-term grid events, that they don't have interfere with the protection schemes in place by the utility at distribution, subtransmission, and transmission. And so there's some consideration of that present in the timeframes around ride through. So interesting to note that even after all the inclusion of the smart grid aspects, a lot of the main concerns still fall back to some of the fundamentals of 1547. And again, the backstop for 1547 remains that if the grid remains out of defined frequency and voltage limits, a DER must get off the system and stop energizing the power system until itself measures that the frequency and voltages have returned and remained within the allowable range. Again, the default is 5-minute monitoring period, but that monitoring period can be shortened. So I do want to emphasize with all the addition of the smart grid bells and whistles and capabilities, um, that backstop of if there's a sustained grid issue, not just an outage, but if voltage or frequency are out of range, the DER must get off. More along the regulatory lines, what are the concerns? And here's one for you all. Authorities governing interconnection requirements. And I hope I'm correct in my interpretation. If all the 17 distribution utility companies are referring to the common PUC published 5.500, that's a great streamlining asset. In the other jurisdictions I've worked, each investor-owned utility creates its own um, interconnection tariff rule, then gets uniquely approved. Now there's consistency across them typically. Um, but the point being, one change of the 1547/2018, which through your reference of the latest version, you are doing, someone's going to have to select which performance characteristic applies to your jurisdiction. Here's one comment, opinion. If you leave that open, it leaves room for over aggressive requirements, not necessarily needed yet. Um, but it can be used as a way to sort of throttle the rate of interconnection and devices getting online. So I think it's an area where better for all stakeholders to get together and determine how aggressive do you want to get with the reactive and ride-through requirements. It's another way to look at it. And this is emphasizing, again, IEEE doesn't get into how you adopt it, how you apply it. We're here to really answer, well, what are the requirements as called out? But it's such a big issue that IEEE has created this graphic just to show that, these stakeholders are gonna have to get together and select what category. IEEE, again, and I'm very supportive of this concept. Um, Category 1 is really there to accommodate equipment, some of the rotating machines that, for example, don't have the ability to cease energizing a connected power system without physically disconnecting. 2 and 3 are there that really do open up the kind of ride through voltage support that mainly inverter-based systems can deliver today. I do want to highlight that the level 2, which is the mid-level of performance aggressiveness, um, the more aggressive requirements is consistent with NERC PRC 24, the bulk system ride through curves. And that's one issue is I'm sure you're working with your upstream transmission entities. But whatever ride through requirements you set at distribution do need to consider, are they consistent with the bulk power system ride through requirements? That level 3 is appropriate for very high penetration markets where the requirements get more aggressive. A lot of the allowable range of adjustability gets opened up for very low inertia, very high penetration scenarios. And that's where I think, in my opinion, 2 is a great starting point. 3 has to be given some consideration. because it does put some extra burden on all stakeholders. I do want to point to a couple, we'll call it good or even best practice source requirement docs for UL 1741 SA and SB are good hints. And I was looking around at them, and probably a more California Rule 21 and Hawaii Rule 14 are designed a bit more for high penetration scenarios, but National Grid's source requirement document, um, it's public and it might be a handy follow up, is more along the lines of level two. And I think they might even call level two out. But this just gives a good idea how, oh, there's Hawaii Electric. This gives guidance on within these ranges of adjustability and these control options. It gives UL and all interested participants, either designing systems or manufacturing systems, it spells out exactly what are the default settings, ranges of adjustability within that design community jurisdiction. So I just want to point out that coming up with an SRD for your jurisdiction is something worth considering. The California Energy Commission's inverter list is great as even a resource that other state entities, other jurisdictions will even point to at different levels of formality as a way to certify, well, is the equipment proposed verified? Has someone verified that they actually certified to perform? I think I've got that one up. And what's handy in terms of energy storage, within the last couple of years, they added a list of energy storage system inverters. They're really, the issue is it's self-reported, but there's some compliance verification to make sure that these inverters are in fact UL 7041 certified. This is nothing new to your community, given the really strong enhancement to some of the screening and studies guidance here, pending updating rule calls out. But these still might hold some good ideas on some of the devil in the detail stuff of screening, what may trigger a study, what may not. But again, looks like your proposed ruling well thought out for your local needs. A comment on what's the outlook for interconnection standards? A real appealing progress point on the standards front is the publication of a transmission interconnection standard for inverter-based resources. That's the IEEE 2800 2022. Fortunately, there is strong consistency, if not outright matching, and some of the key terminology and how it's defined and measured between 2800 and 1547 2018 issues terminology like cease to energize versus trip, um, the maximum rate of change of power output, consistent between the two. And 2800 being done a little later, talking to the folks that manage that, they don't see a need to do a 2800.9 like we did for 1547, because they approached it and all of their requirements are in context of 4 quadrant capable devices. So the expectation is, off the shelf, it's ready to be applied for energy storage. So that teeter totter in the middle is a good description of, for those who work on standards, it's always, this balancing. We don't want to hamper innovation and change by maybe oversimplifying, and by oversimplifying, constraining the options that otherwise could be offered up between all parties. And I'd say this is in large part, bulk grid perspective on getting interconnection standards more in alignment with newer challenges like low inertia systems that have deeper frequency excursions and longer frequency recovery timeframes. Yeah, the rider is really going to come in handy. There are already numerous recorded events where, let's say, an area-wide deep voltage dip knocks off a whole host of DER. One of the results is whoever's responsible for frequency sees an aggressive voltage dip that was impacted in part because there was a big chunk of DER that left the grid. And a lot of times there's no visibility because, in my experience, a lot of markets still treat DER as a net load or net of load. They're not an active resource injecting anything, they're just removing load. I think the world needs to change a bit to not see them as just netting load, but actually as a grid connected resource with some grid voltage and frequency support capability. What's going on? So this is looking forward. The P1547 revision is active. My opinion at this time is it's mainly cleanup to deal with a couple errors in 1547 2018 and a lot of focus on cleaning up the testing requirements. So the 1547.1 test procedure and UL 1741 certification processes can be adjusted a little bit to remove some unintended complexity. A 1547 guide for intentional islanding, i.e. microgrids. Microgrids as a form of intentional islanding being just started. So here's an opportunity for those who do like to do standards development. It will be a 2 to 3 year project that's in its first, it just held its kickoff meeting. And these should, PDFs of this can be shared, Dylan. This is all public IEEE stuff. Hopefully those links take you right to the project pages. And there's a recommended practice for DER gateway, that interface between the distribution system and the DER project, getting more specificity about how that, what are the capabilities. And that'll also get into more detail on what specific information objects, information models can, their usage, of course, bounded by the three protocols called out in 1547. I want to go back to, you got an appealing area of your updated rule that, see if I find the right rules. Basically, controlled base project power ratings. You open up the potential to use that, which is really at the I'll call the front end of adoption. Not all folks adopting 1547 2018 are taking advantage of the fact that 2018 really clarifies a bit that you can do a system rating and a system compliant at the point of common coupling, and it doesn't have to be the aggregate rating of each individual nameplated unit, and you don't necessarily have to push down the compliance if you truly have a compliant system interface with the appropriate isolating capability. You fall somewhere in the middle. I think you still require compliance out through the individual devices like the inverters, even if you have a system. But again, given your local needs and stakeholders, I'd say that's a good starting point. Uh, but it's a little bit of belts and suspenders versus going full system capability. Now, here's one of the devil in the detail. I couldn't read from the ruling whether that export capability limit using controls or a system like a project level controller also applies to the power rating at the interface. Because one issue that really is coming up that I've seen a number of times, and again, not just me, this is an IEEE slide, is especially for retrofits where there's a solar system that adds an energy storage. Is that a material change? Well, if your criteria is based on total plate capacity behind your point of common coupling, it certainly is. And it opens up, reapproving, re-reviewing, potentially resetting your whole interconnection. A couple ways to address that is you can DC couple behind a single common rated inverter, Or you can evaluate whether it's appropriate for your market to let control-based export limits also apply to the power rating of the project connected at your point of common coupling. DC coupled inverters are more and more present in the market. And an interesting aspect on that, I'm seeing most of those come through the V2G inverter folks, where they'll have multiple DC ports behind one AC conversion device that you can connect stationary storage, PV, as long as 1 through X number of electrical vehicles on the DC side. And that's a clean way to do it. And it also is a clean way to do it for ITC, the federal tax incentive. A whole host of, for those who really interested and want to dive deeper, some links outside of IEEE. EPRI can get into more specifics on how a specific jurisdiction interprets and implements and monitors 1547 NRECA. Has some really good references. So point to that. I also want to share my opinion that the national labs, Sandia, for example, another case where I'm limited as an IEEE volunteer. Folks like Mike Roth wearing his Sandia hat can get into more specifics about your jurisdiction. Again, that caution on UL 1741, they don't append it with a date. They add these supplemental appendixes. So if you just call out UL 1741 generically without the supplemental amendment, it is not compliant with 1547 2018, which is the latest version with all the smart inverter capability. So just to point that out, SA, that supplemental amendment designed around Hawaii Rule 14 and California Rule 21 is pretty mature. And there's, I'll say, multiple vendors already have certified their energy storage and PV inverters to that standard. And SB is starting to catch up. But I'd like to highlight that SA delivers the core smart grid capabilities as well as some of the information exchange that you get in SB. So as an interim, it's a great worth considering as a specific level of UL 1741 to require, and it won't tie your hands if and when you would elevate that to SB. There are no conflicts and there's high consistency. SB just goes a little farther. Since you are calling voltage ride through and frequency ride through, the backup slides go through exhaustive detail for those who are interested on what are specifically the ranges of adjustability, a deeper dive into what is the terminology, really a standard developed by engineers. Again, you'll get PDF copies of this for those who can use the extra information. I looked at the Burlington, I think it's called Electric Department, in case they had a network distribution. I couldn't find if there is or isn't network information distribution, but there are some clarifications of 1547 2018 really relevant to getting DER connected to networked and secondary network distribution if any of your utilities have that. And that's already been applied to good effect to get some PV and actually some creative enhanced outage recovery schemes deployed on network distribution. A little bit more background on what that interoperability chapter is in 2018. And that's it. I'll stop sharing, Dylan.
All right. Thank you so much, Charlie. That was great. Appreciate it. Looks like we got a couple of questions for you in the chat. I've got a two-parter here from Brian Evans Mongion from the Village of Hyde Park. So I'll start with him. Firstly, he asks, given the evolution toward a bidirectional operating grid, do you see that we will need to alter grid protection systems to protect from events or device failures from the DU footprints as well as the centralized dispatched approach in the past? If so, how do we ensure that commissioning and interconnection requirements are changed to keep protection at all levels?
A good question. So, a little bit I've seen from people who are much more involved in this, that um, the biggest change from to the future power system. Oh, let me go ahead and display again. Is the reduction in short circuit duty. So as you get more of these distributed bidirectional devices, in I guess you could, some ways, offsetting the loss of traditional generator, one specific and impactful to protection scheme impacts is loss of fault duty that is critical to operating a time over current based protection regime. And hopefully this makes sense. Uh, but the, the degree of loss of inertia at this point, the ability to coordinate all the way down to, let's say, the feeder fuse, due to the impact of a DR up through a recloser to an upstream breaker across a transformer, that traditional time over current regime is still working. That in part also helps assure that we don't need this direct transfer trip in all cases to assure anti-islanding. So in the near term, traditional protection approaches and schemes, although the let's say the engineering required to maintain that coordination is going to get tougher, and it may require going to some electronics versus, for example, fusing relays and breakers. Not solid state breakers. You can stick with conventional, but some smart relays. There will come a time where, let's say, traditional protection approaches will have to be revamped. Share an opinion. I think if traditional protection schemes became stranded investments, that could be an example of an unintended big impact to the interest industry that could have rate impacts even.
Awesome.
Next,
Great.
Dylan.
Great. Thanks, Charlie. Appreciate it. All right. Looks like I got one more for you in the chat, and then we can pass it to John to close us out. But Vidya Venkala, sorry, from the British Columbia Institute of Technology asks, what is the current status of 1547 as a mandatory standard across states? Last checked, several AHJs had their own portions of 1547 in their localized interconnection standards. Is there a new map of the status of mandating the use of all 1547 for all states?
Irika has a really good um, summary of that. I'll see if I can find a link and put in the chat. But the vast majority, again, jurisdiction is for those that are regulated by a state PUC, primarily investor-owned utilities. It's very ubiquitous that 1547 is adopted, but typically with exceptions. The big one being galvanic isolation, a lockable visible disconnect switch. So in my experience, that's the big addition that a lot of states will add within their specific jurisdictional tariff rules that goes above and beyond 1547. But by and large, and even among the 2,800 plus smaller utilities, many public, um, my experience is 1547 is either in their rules, in a state rule they can point to. In some states like Montana, they even have it within legislation. So all their small public utilities that don't have the wherewithal to create and maintain their own interconnection standard can at least point to a reference, and sometimes a process gives guidance on the application to approval process. In all of those I've seen, 1547 is called out. Thanks to this work long ago.
Great. Thank you so much, Charlie. Looks like we are at that time, so I want to give a big hand to both you, Charlie, and Chris for taking the time to talk to us today. Really do appreciate it. If anybody needs their contact information, feel free to reach out. The slides and presentations will be posted on our website, and the recording will follow. It'll take a little bit longer just because it has to go through our review and approval process, but it will be up on the website externally to view at a later time. I want to hand it off back to John Cotter to close us out and talk about next week. John, the floor is yours.
Thank you, Dylan. I would like to thank also Chris Searles and Charlie Vartanian for their presentations today. I know that was a lot of information in a relatively compressed time frame, so I hope it proves helpful to everyone that was in attendance. Would like to thank Dylan again for running our platform for us and keeping things going as smoothly as he does. So with that, we conclude our second session in our 5-part series. I'd like to thank everyone for attending, our presenters and the folks at Sandia for their assistance. The third session will take place next Thursday, November 16th, again from 1 to 3 p.m. Eastern Time. Next week, we will have the second part of our 2-part presentation on the installation and operation of energy storage systems. More detailed information on next week's agenda, as well as the agenda for all of the remaining sessions, can be found in the Commission's order announcing this series using the Commission's online case management system, EPUC. The document can be found in EPUC at case number 21-3883-rule, and then selecting the tab for Commission issued documents, and then selecting the document dated September 29th, 2023, titled Order Announcing Webinar Series. We thank everyone for their attendance today, and we hope to see all of you again next Thursday. We are concluded for the day. Thanks again.
Thanks, everybody. See you next time.